Greetings, Math 347 fans. In this video, our goal is to review some important concepts from calculus that end up being important in this class too. In particular, we'll talk about integration by parts, integration by partial fraction decomposition, and improper integrals. So starting off with integration by parts. I'll remind you of the integration by parts formula. The integral of u dv is u times v minus integral of v du. Of course, this is a formula for indefinite integrals, but definite integrals work similarly. So the strategy from Calc 2 is to choose u and dv, then compute v and du, and I always recommend that students should make sure that the new integral doesn't make your life worse. Just as a reminder, there's a real quick derivation of the integration by parts formula just from the product rule. So if you write the product rule in differential notation, the derivative of u times v is the first times the derivative of the second plus the second times the derivative of the first, and then integrate up both sides. You can quickly get the integration by parts formula. Okay, so an example, a definite integral here, the integral from 0 to pi over 2 of x cosine x dx. So we'll let u be x and dv be cosine x dx, and of course from that we can compute that du is dx and v is sine of x. So the integration by parts formula gives us the value of the definite integral in terms of a new integral, which is easier to compute than our original. So as you can see here, the value of the definite integral ends up being pi over 2 minus 1 after application of integration by parts. You might remember that some integration by parts requires multiple applications. So in this example, we let u be x squared, dv be e to the minus x dx, and find that du is 2x dx and v is minus e to the minus x. Integration by parts formula gives us the desired antiderivative in terms of a new antiderivative, which I claim to you is a better situation than before. So here's a scenario where we apply the integration by parts formula twice. On this new integral, we let u be x and dv be e to the minus x dx. And of course, this leaves us with an integral of minus e to the minus x that we can quickly evaluate to come up with an expression for an antiderivative of this. Of course, being an indefinite integral here, we'll associate this with the general antiderivative and tack on a plus c at the end. In this example, we see that integration by parts can be applied twice, reproducing the original integral. So if we let u be sine of 2x and dv be e to the x dx, we can from that compute du and v, and this is a case where the new integral is no worse than the original integral. So applying integration by parts again, let u be the cosine, the trig function, cosine of 2x dx, and dv be e to the x. And we can see here that once we do this, we've reproduced the original integral of e to the x sine of 2x. Now, of course, this is an equality, and we can manipulate this equation algebraically, adding our factor of negative 4 times the integral of e to the x sine 2x to both sides. So once we do that, we have an expression for 5 times the desired integral that we are able to just divide both sides by 5 to get an expression for the desired integral. Many students use tabular integration by parts, and that's a good strategy in this case too. And if you are comfortable with tabular integration by parts, I recommend you use that. Okay, talk a minute about partial fraction decompositions. So I'll remind you that the main strategy of a partial fraction decomposition is to decompose a rational function into portions involving factors of its denominator to make those portions easier to integrate. So in this class, we'll encounter sort of two common flavors of partial fraction decomposition. So the first one is linear distinct factors. You probably notice that the denominator in this case can factor into distinct linear terms x times x plus 3. And of course, the form of the partial fraction decomposition in this case is some unknown constant a over x plus another unknown constant b over x plus 3. Clearing the denominator, we see that 1 is equal to a times x plus 3 plus b times x. And this is a case where you can choose wisely to identify those constants a and b. So as x approaches 0, we're left with 3a is 1, or a is 1/3, and as x goes to minus 3, we're left with negative 3b is 1, or b is negative 1/3. So there's the decomposition. 1 over x times x plus 3 is 1/3 times 1 over x minus 1/3 times 1 over x plus 3. Now, of course, if we wanted to evaluate an indefinite integral, we can just use that partial fraction decomposition to do so. So from the decomposition, we can see that the rational function is equal to, again, 1/3 1 over x, 1/3 1 over x plus 3, and those both integrate quickly like natural logs. And if you were in a Calculus 2 class, you would probably stop having written this expression as just a difference of natural logs. It turns out that we'll often be able to simplify expressions by applying rules of natural logs. So in this particular case, we'll express the difference of natural logs as the natural log of the quotient, x over x plus 3. A second flavor of an example is an irreducible quadratic factor. So in this particular case, the denominator factors as x times x squared plus 1, and that factor of x squared plus 1 is an irreducible quadratic factor. So you'll remember that the distinct linear factors in this form have a decomposition term that is just like what we saw before, whereas the irreducible quadratic factor has a numerator that looks like bx plus c over x squared plus 1. Again, we can clear the denominator and express this equation as x plus 1 is equal to a times x squared minus 1 plus bx plus c times x. And once again, a wise choice of x allows us to quickly solve for one of the constants. Now, it turns out that those wise choices of x aren't as easy for quadratic factors, so it's often convenient to equate coefficients, multiplying out the quadratic on the right-hand side and coming up with a term that looks like a plus b times x squared plus c times x plus a. Now, of course, if that quadratic in red is to equal x plus 1, the coefficient of the x squared term has to be 0. And since we already know that a is 1, that gives us b is negative 1. Similarly, the constant coefficient has to be equal to 1, so the quantity c is equal to 1. This gives us our decomposition that x plus 1 over x cubed plus x is equal to 1 over x minus x over x squared plus 1 plus 1 over x squared plus 1. And again, there we've just separated the two terms in the partial fraction decomposition for the irreducible quadratic into a term involving x and a term involving the constant. So again, if we want to integrate a rational function involving an irreducible quadratic, we can do that with a partial fraction decomposition. Of course, the first term integrates quickly like the natural log of x. The second term integrates like the log of x squared plus 1 with a quick u substitution, and you'll probably remember that 1 over x squared plus 1 integrates like the inverse tangent function, the arctan. Finally, we'll discuss improper integrals. So I'll remind you from Calculus 2 that integrals may be improper if either the integrand is discontinuous or there's an infinite limit of integration. In this class, we'll see improper integrals due to an infinite limit of integration. Just a reminder of terminology, we rewrite this integral as a limit of a definite integral with finite limits of integration, and then if the limit exists, we say that the integral converges, and otherwise we see that the integral diverges. In this class, we will usually be interested in integrals that converge. So an example of an improper integral, the integral from 0 to infinity of x squared e to the minus x. We'll start by rewriting this integral as the limit of an integral with finite limits. So the limit as t goes to infinity of the integral from 0 to t of x squared e to the minus x dx. And then this is an antiderivative that we found in our section of integration by parts, so we'll go ahead and just use that antiderivative we found there to express the antiderivative of x squared e to the minus x as negative quantity x squared plus 2x plus 2 times e to the minus x. Plugging in the upper and lower limits with the fundamental theorem of calculus, we now have a limit involving t as t goes to infinity. Now, of course, there's going to be part of this limit that goes to infinity and another part that goes to 0, so we can use L'Hopital's rule to evaluate that limit, rewriting it as a quotient. Application of L'Hopital's rule twice tells us that that limit is 0 of the rational function times the decreasing exponential, so we say that this integral converges with a value of 2. Okay, hope you enjoyed this brief review of Calculus 2. We'll have problems that involve integration by parts and partial fraction decompositions, as well as improper integrals that come out throughout the term.